Hi, my name is Alice, and today I'm going to be talking about a topic in chemistry, specifically solving problems with Lewis dot structures and VSEPR structures, so stay tuned. Alright, so for this sample question, basically it has two parts. The first is to draw the best Lewis dot structure for each molecule, and then name the electron geometry and molecular shape. If you remember, that's from VSEPR, and that's where that comes in, for each of the following species. So there are 9 that we're going to be looking at today, and of course you should be able to do this with any species at all. Okay, so before we actually start getting into it, I want to make sure that we know exactly what we mean by the different terms. So the first term is the Lewis dot structures, and we'll see some examples of them if you can't remember it exactly right away. But basically they're representations of the bonds and lone pairs of a single molecule or a single whatever it is that you're looking at. Okay, and as an example, NaCl, or common table salt, looks like this. So you can see Na, which does not have a bunch of valence electrons. It just has the single bond to the chlorine atom, which has the 6 unbonded electrons and the 1 bond to the sodium. And then VSEPR, I will link down the explanation video that I have made about the VSEPR system and how to use it down below, so you can check that out. But basically it's a system that helps you predict the shape of a particular molecule. And when you're talking about VSEPR, for this particular molecule, both the electron geometry and the molecular shape are linear. Okay, so let's get into it. First example is VSEPR, aka beryllium and fluoride. Okay, so when we start to work these problems, basically you want to look at just the valence electrons and how many bonds each pair or each atom has. So here, beryllium starts off with 2 valence electrons, and each fluorine atom has 7. So when you put them all together, it looks like this, very standard. And since there are no lone pairs on the beryllium, that means that the electron geometry and the molecular shape are the same. And this is going to hold true for any atom, any molecule that doesn't have any lone pairs. The electron geometry and molecular shape are going to be the same. In this case, linear. Alright, so BCl3. This is boron and chloride. So boron has 3 valence electrons, and each chloride has 7. And so when you put those together, it's going to look exactly the same, or not exactly, but very, very similar to what we just saw. So here you have the Lewis dot structure. Again, you can see the 3 valence electrons of the boron in the center, and the 7 valence electrons of the chlorine all around each of those. And again, because there are no lone pairs on the boron, the electron geometry and molecular shape are the same, and both of those VSEPR shapes are trigonal planar. Alright, the next question that we have is carbon tetrafluoride. Tetracarbide, sorry. So you have carbon in the center surrounded by 4 chlorine atoms, and you have 4 valence electrons for the carbon and 7 for each of the chlorine atoms. And when you put them together, these all sort of follow the same pattern here, so it's very similar. And just as a reminder, I have the regular bonds here represented as like straight normal lines, top and bottom, and then the 2 sort of different lines on the sides represent the sort of 3D modeling of what this actually looks like. So The dotted line on the left is the means that the chlorine there is sort of goes into the page, and then the wedge on the right means that that chlorine actually comes out of the page. So you can sort of imagine what that looks like in 3D. And again, there are no lone pairs on the carbon, which means that the electron geometry and molecular shape are the same. In this case, tetrahedral. Okay, so sort of going along the same lines, you have phosphorus, which has 5 valence electrons, and Br, which has 7. So put that together, it looks like this. Again, the wedge and the dotted line sort of help you visualize exactly what that looks like in 3D. And there are no lone pairs on the phosphorus in the middle, which means that both electron geometry and molecular shape are trigonal bipyramidal. Okay, and sulfur and iodide. You have the sulfur with 6 valence electrons, which create bonds with each of the iodide atoms, and this is what that looks like. So no lone pairs means that this is octahedral. Remember, anything with 6 atoms surrounding the center is going to give you an octahedral. All right, so when you actually get to molecules with lone pairs, it becomes a little bit trickier, but it's still the same concept. So here, BH2 negative. Don't ever forget that there is that negative, which means that you have to have that extra electron. So here, boron has 3 valence electrons, and each hydrogen has 1. But instead of having just 1 lone electron here, it does have the pair because of that negative charge. So that's the thing that you have to be mindful of. And since we have that lone pair, the electron geometry and molecular shape are different. So you can see the electron geometry, which takes into account the lone pair, is trigonal planar, whereas the molecular shape, which is what the molecule actually looks like, here is bent. All right, Ni3. So this is tricky because there is a lone pair here, but you can't really tell because there's no plus or minus charge. And actually what it looks like is this. So remember, the dotted line and the wedge gives you the 3D shape. You can sort of see what it might look like there. And because there is that lone pair at the top here, you can see that the electron geometry is tetrahedral. But when you're actually looking at the molecular shape itself, it's just trigonal pyramidal. It's ClF4 plus. So again, the plus minus the charge probably gives you an indication that there's going to be a lone pair somewhere on this molecule. So when you put together what this looks like, this is actually what you get. And you can see here that chlorine is supposed to have a total of 7 electrons near it, but you can see it has 4 from each of the bonds with the fluorine atoms, and then a lone pair, which actually totals to 6 valence electrons. And that's where that positive charge comes from. So you can see that that it is just a little bit different. And because of that lone pair, again, you have a different electron geometry and molecular shape. In this case, the electron geometry is trigonal bipyramidal, and the shape is a seesaw. So now we come to the last example that I have, so bear with me. SF5 minus. So with this, we start out with the knowledge that sulfur only has 6 valence electrons and each fluorine has 7, so that's not as important. But when you put together all of these atoms into the molecule, this is what you get. So if you take a look, sulfur has 1, 2, 3, 4, 5 bonds with the fluorine atoms, which means that it has 5 valence electrons near it. And then it also has 1 extra. But because the entire molecule has a negative charge, you can see that there's an extra electron near that sulfur. So that again is what gives it that negative charge. And because there's that lone pair, you have different electron geometry and molecular shape. So one is octahedral, the other is square pyramidal. All right, so that's pretty simple. Hopefully that gave you a better idea of how to answer questions that are related to Lewis dot structures and VSEPR and how to get an idea of both of those from creating the Lewis dot structure. Now, if you're interested, I do offer all of my slides for free, plus other bonus materials. At that link, you can find it down below, and definitely check that out if you want. Otherwise, I've got some other videos there, and I hope you can check those out and that they are useful for you. If you found this helpful, I hope you can share it with anyone you know, your friends, your classmates, people that you hate even. And if you have any questions that I can help you answer, just leave a comment in the comment box below and I will get to you whenever I can. Thanks so much for watching, and I'll see you later.